Lesson 4.1 covers graphing linear inequalities and systems of inequalities. Let's first look at graphing single linear inequalities. Well, if you remember from previous lessons, the standard or the general form of a linear equation is ax plus by equals c. And if you remember, the solution to a linear equation is every point on that line. Linear inequalities are obtained by replacing the above equal to sign with an inequality symbol. So there's four forms for a linear inequality. I could have ax plus by is less than c, ax plus by is less than or equal to c, ax plus by is greater than c, and finally ax plus by is greater than or equal to c. I just replace the equal to sign with any of the four inequality symbols. When we graph linear inequalities, there's two parts, the boundary line and the shaded area. Let's first look at the boundary line. The boundary line is simply the linear equation associated with the linear inequality. If you're given the linear inequality, what you're going to do is replace the inequality symbol with an equal sign to get the boundary line. And these boundary lines are just linear equations that we've graphed in previous lessons. The one thing you have to keep in mind is whether the boundary line is included as part of our solution or whether it is not. Well, the boundary line is solid and is part of the solution if the inequality has an equal to portion to it, if it's greater than or equal to or less than or equal to. The boundary line is broken and is not part of the solution if the inequality symbol does not have the equal to line under it, if it's just greater than or just less than. And then do keep in mind, when possible, use the intercepts to graph the boundary line. In the next couple of lessons, we're going to be using those intercepts further in our problem, and so just to develop the habit, use the intercepts so that you'll get used to graphing with them. Next, let's look at the shaded area. That boundary line divides our plane into two portions. With linear inequalities, the shaded area is a half plane, and these half planes are basically half of the rectangular coordinate system. And then we're going to determine in this class which side of the boundary line to shade by using a test point. There are other methods. I'm just going to stick to the test point method. Now, when we're using test points, first we pick any point on either side of the line. All you've got to do is make sure that test point is not a point on the line. And it doesn't matter which side of the line you get your test point from. Then we're going to plug that test point into the original inequality. If we get a true statement, we're going to shade the side of the line not containing the test point. And if we get a false statement, we're going to shade the side of the line containing the test point. Now, if you've graphed linear inequalities in other courses, this is the opposite of what you've done. I do my shading a little bit differently. So this warning is for my class only. In this lesson and the next two lessons, we're going to be graphing several inequalities on the same graph. Once all the inequalities are graphed, we're going to have to determine which portion of the rectangular coordinate system was shaded by all the lines. Well, in the past, I've watched my students struggle to find this region, especially when you get 4 or 5 lines graphed. It's really hard to determine what area has been shaded every single time, what area was covered by every single line. And so I found a way around this. I've got another method that I use for shading that makes this final solution area a lot easier to determine. In this class, instead of shading the part that is the solution, which is what most teachers and almost every book does, we're going to mark out what's not our solution. And this way, the portion of the graph left without a single mark over it is going to be the solution. One other topic I want to cover is bounded and unbounded regions. If the feasible solution area, and we'll discuss this later, is totally enclosed by boundary lines, then it's said to be bounded. Otherwise, the feasible solution area is said to be unbounded. If there's a part of that solution area that's not enclosed by a line, then the solution area is unbounded. So let's look at some examples. I want to solve and graph the following inequalities. So I have 5x minus 2y is greater than or equal to 10. So let's begin by first listing our boundary line. Our boundary line is 5x minus 2y equals 10. And then one thing you want to note is since I had an equal to in my original inequality, this is going to be a solid boundary line. Now I simply want to graph this line using the intercepts. So for my x-intercept, if you remember our shortcut, for the x-intercept we let y be 0. So if y is 0, this entire term is 0. So cover it up with your finger or your pencil. And you end up with 5x equals 10. If I divide each side by 5, I get that x equals 2. So my x-intercept is the point 2, 0. For my y-intercept, let x be 0. If x is 0, 5 times 0 is 0, so this whole term becomes 0. So cover it up, and you have negative 2y equals 10. Divide by negative 2, and you get y is negative 5. So the y-intercept is the point 0, negative 5. If I graph these points, I have 2, 0, and 0, negative 5. My boundary line was solid, so draw a solid line through those 2 points. Now that line is dividing my coordinate system into 2 parts. I've got the part to the left of it that includes the origin, the point 0, 0, and I have the part to the right of it. So I've got to decide which half is my solution. So I'm going to do this with a test point. And if at all possible, always test the point 0, 0. It's just the easiest one to use. So go back to the original inequality, 5x minus 2y is greater than or equal to 10, and plug a 0 in for x and y. When I plug zeros in, my entire left-hand side is just going to be a 0. So I get 0 is greater than or equal to 10. That's false. Since 0, 0 was false, that means every point on this side of the line is going to be false. And you could test, you could plug in negative 3, 2. You could plug in negative 4, negative 2. Any point from this side of the line that you plug in will give you a false statement. So this side is not our solution, and the right-hand side is our solution. As I mentioned before, most books will shade the part that is your solution. In this class, I prefer to mark out or shade the side that's not our solution. So my shaded area is sort of marking it out. That's not our solution. So everything left unshaded is our solution. So I'm just going to write the word solution there. And I encourage you to put that in your notes just so you'll get used to that the unshaded part is our solution. Since this boundary line was solid, it's part of our solution also. So our solution is every point on this line and every point in this unshaded area. If I plug any of those points back into my original inequality, I'll get a true statement. Let's look at the next example. I have 3x plus 4y is greater than 0. So I'm going to begin with my boundary line. So I take the inequality and replace it with an equal sign, and I get 3x plus 4y equals 0. Now look back at your original inequality sign. It did not have an equal to sign under it. It was just greater than, not greater than or equal to. So that means this boundary line is going to be broken. It's not going to be part of our solution. Now I want to graph this boundary line, and if possible, I want to use my intercepts. For the x-intercept, let y be 0. If y is 0, then this entire term 4y becomes 0. So I get 3x equals 0. And if I divide by 3, I get x equals 0. So my x-intercept is the point 0, 0. Well, for my y-intercept, let x be 0. If x is 0, then this entire term 3x becomes 0. So I end up with 4y equals 0, so y is 0. Whenever your x and your y-intercept is 0, 0, you've got to have a second point to graph this line. So for my second point, let either x or y be any number. A trick that I use to avoid fractions is I let x be the coefficient for y. Since there's a 4 in front of the y, I'm going to plug a 4 in for x. And this will just help me to avoid having to graph fractions. So if x is 4, I have 3 times 4 plus 4y equals 0. That's 12 plus 4y is 0. Now if I subtract 12 from each side, I get 4y equals negative 12. And then finally divide each side by 4 and you get y equals negative 3. So my second point is the ordered pair 4, negative 3. So to graph my boundary line, I'm going to graph the points 0, 0 and 4, negative 3. Now this is the part that you have to really remember to do. Since my inequality was not equal to, this is going to be a broken boundary line. So don't draw a solid line through those points, but instead draw a dashed line or a broken line through those points. That's our way to show that the boundary line is not part of our solution. Now I need to pick a test point to decide which side of that boundary line is our solution. I usually like to pick 0, 0 for my test point, but since 0, 0 is on the line, I cannot pick it. So for the test point, pick any other point on the graph, as long as it's not on that line. So I'm going to pick the point 5, 0. I know the point 5, 0 is on my x-axis, so I'm going to pick it. So go back to the original inequality, 3x plus 4y is greater than 0. Plug a 5 in for x and a 0 in for y. And if I do this, 3 times 5 is 15, and 4 times 0 is 0. 0 plus 15 just gives me 15. So I have 15 is greater than 0. That's a true statement. So since the point 5, 0 was true, that means every point in this area, sort of, you can look at that as being above the line. Every point above the line is going to be true. It's going to be part of my solution. So that means the area below the line is not part of my solution. So the area that's not our solution, we're going to shade it or mark it out. So that means my solution is the area that's not shaded. This time my solution is just the unshaded area. The line is not part of my solution. Well, in the next couple of examples, we're going to look at graphing systems of inequalities. So the first example, I have 2x plus 3y is less than or equal to 12, and x minus y is greater than or equal to 3. This time I'm going to consider both of my inequalities and find the boundary lines for those. So my first boundary line is 2x plus 3y equals 12. My second boundary line is x minus y equals 3. To find the boundary line, you just replace the inequality symbols with equal signs. Both of these boundary lines are going to be solid because they were both equal to in the original inequality. So let's find the x-intercepts for the first one. In the first equation, for the x-intercept, let y be 0. So if you cover up the y term, you end up with 2x equals 12. And if you divide by 2, you get x equals 6. So my x-intercept is the point 6, 0. For the y-intercept, let x be 0. So if x is 0, cover up the x term, and you have 3y equals 12. Divide each side by 3, and you get y equals 4. So my y-intercept is the point 0, 4. And as we mentioned, because the original inequality sign had the equal to with it, this is going to be a solid boundary line. Next, let's look at x minus y equals 3. For the x-intercept, let y be 0. So I have x minus 0 is 3, or just x is 3. So my x-intercept is the point 3, 0. For the y-intercept, let x be 0. If x is 0, this leaves me with negative y equals 3. So if I divide each side by negative 1, I get y is negative 3. So my y-intercept is the point 0, negative 3. And again, this is a solid boundary line because the original inequality had the equal to part. So now let's graph these boundary lines. For the first boundary line, plot the points 6, 0 and 0, 4. And draw a solid boundary line through them. Now you can either shade at this point or graph the other boundary line and then shade. It doesn't matter. I'm going to go ahead and shade this one. If you do shade before drawing the second boundary line, be sure you shade light enough to where you can still see the graph underneath it. So for this line, I can test 0, 0 because the boundary line does not go through the point 0, 0. So go to the original inequality, 2x plus 3y is less than or equal to 12, and replace x and y with zeros. When you do this, this gives me 0 is less than or equal to 12. And that's a true statement. So since 0, 0 was true, it's part of my solution. So every point below the line is part of my solution. Since this area is my solution, the area above the line is not my solution. So I mark out what's not my solution. For the next line, I'm going to plot the points 3, 0 and 0, negative 3. This is also a solid boundary line, so draw a solid line through those 2 points. For my second line, I can also test 0, 0 since that boundary line does not go through 0, 0. So go to x minus y is greater than or equal to 3. And replace the x and y with zeros. When you do this, you get 0 is greater than or equal to 3. This time, that's a false statement. 0 is not greater than 3. So for the second boundary line, 0, 0 is not part of my solution. So the whole area to the left, or you could look at it as being above that boundary line, is not my solution. So I'm going to shade it to mark it out. So now if you look at your graph, every every point in the area that's not shaded is my solution. So I just sort of drew a box around that to show you that this is my solution area. Now be careful. My box, I put a vertical line here and the horizontal line here, but the shaded area doesn't end there. It keeps on going. I just boxed in what was on my grid. That is my solution area. Every graph that I've put so far would be considered unbounded. Now I drew this box in, but like I said, this vertical part continues on forever, and this horizontal part doesn't. My solutions don't stop there. It continues on forever. So there is no boundary lines right here. So this is an unbounded solution area. Let's look at the next example. I have x plus y is greater than or equal to negative 1, and x plus y is less than or equal to 5. So let's begin with our first boundary line. X plus y equals negative 1, and our second boundary line will be x plus y equals 5. So the intercepts for my first boundary line, for my x-intercept, let y be 0. If y is 0, I get that x is negative 1. So I have the intercept negative 1, 0. Then for the y-intercept, let x be 0. So I have 0 plus y, or just y, equals negative 1. So my y-intercept is the ordered pair 0, negative 1. Since the original inequality did have the equal to mark under it, this boundary line is solid. Now for x plus y equals 5, for the x-intercept, let y be 0. So that gives me x plus 0, or just x equals 5. So my intercept is the point 5, 0. For the y-intercept, let x be 0. And that leaves me y equals 5. So I have the ordered pair 0, 5. And since my original inequality was less than or equal to, the equal to part causes this line to be solid as well. So for the first boundary line, plot the points negative 1, 0 and 0, negative 1. And we're going to draw the solid boundary line through these 2 points. Now for my test point. This line does not go through 0, 0, so test 0, 0. Go back to the original inequality, x plus y is greater than or equal to negative 1. If x and y are both 0, that gives me 0 is greater than or equal to negative 1, and this is true. Since 0, 0 was true, every point to the right of, or you could think of it as above that line, is part of the solution. So the area to the left or below the line is not part of the solution. So I'm going to mark out that area. For the next boundary line, let's go to the x plus y is less than or equal to 5. I'm going to plot the points 5, 0 and 0, 5. This was also a solid boundary line, so draw a solid line through those. That line does not go through 0, 0, so I can test 0, 0. Go back to the x plus y is less than or equal to 5. If x and y are both 0, I have 0 is less than or equal to 5. And that's a true statement. Well, since 0, 0 was true, every point to the left of or below that boundary line is part of my solution. So every point above it or to the right of it is not part of the solution, so mark that out. Now you look, the area that is not shaded at all, any part not shaded is my solution area. So I'm just going to write the solution between those 2 parallel lines. Now if you remember, with a system of equations, if these were equal to signs and not inequalities, parallel lines always gave me no solution because there was no point where they crossed. Well, since these are inequalities, I can have a solution if the lines are parallel. This time the solution is the area between the two parallel lines. And as we stated before, since these lines continue forever, even though my graph, my grid is ending here, it really goes on forever. So there is no bound to my solution area here in the top corner or in the bottom corner. So this is an unbounded solution area. For the next example, we have x plus y is less than or equal to -1, and x plus y is greater than or equal to 5. The only thing that's changed from the previous example is I've switched the inequality symbols. So my boundary lines remained the same, which means my intercepts remained the same. So to save us time, I've already listed the boundary lines and the intercepts. And I've also noted that both boundary lines were solid because I had the inequality with the equal to part with it. You also have the boundary lines graphed on your grid already, but let's just look at that first boundary line. Since it does not go through the point 0, 0, I can test 0, 0. If I plug the 0, 0 back into my inequality x plus y is less than or equal to -1, I get 0 is less than or equal to -1, and that's false. So this time 0, 0 was false, so I'm going to mark out the side that contains 0, 0. Every point in that area is not part of our solution. Now for the second boundary line, which is already graphed on your paper, it had the intercepts 5, 0 and 0, 5. I can also test 0, 0. So if I test 0, 0, go back to x plus y is greater than or equal to 5. Plug in a 0 for x and y, and you get 0 is greater than or equal to 5, and this was also false. So for my second boundary line, I'm going to shade everything below it or to the left of it. Now I don't stop at this boundary line, you just ignore it as if it's not there. So that was false, so everything below that line is going to get shaded. Now if you remember, our solution is the area that's not shaded. Well, this entire grid has been shaded, so I don't have an area that's unshaded. So this system of inequalities has no solution. There's not a point on the grid that is true for both equations at the same time. Let's look at some applications of systems of inequalities. We're going to look at more applications in a couple of lessons, but I just want you to see a few examples of how a system of inequalities would be used in everyday life. So with this example, Carla wants to invest up to $40,000 in stocks and bonds. She feels the amount invested in bonds should be at most 1/3 of the amount invested in stocks. What are her investing options? So always when you start an application problem, look at what you need. We were asked for the amount invested in each type of account. This lets us know what we want our variables to be. Since we have two different accounts, we're going to have two different variables. So there's stocks and bonds. So let's let X be the amount of money invested in stocks, and let's let Y be the amount of money invested in bonds. Once you decide what you need and what your variables are going to be, you look back through the problem to find out what your restrictions are or what your constraints are. What is keeping Carla from investing an infinite amount of money? So you read back through the problem and find out what is restricting her investing options. Well, first we're told she wants to invest up to $40,000. So she's limited on the amount of money she has to invest. Well, if I take the amount she invests in stocks and add that to the amount she invests in bonds, then I'm going to have X plus Y. I want that to be up to $40,000. So I'm going to set that less than or equal to $40,000. She can invest less. She doesn't have to invest all of her money. That's why it can be less than $40,000. She just cannot invest more than $40,000, so it cannot be greater than $40,000. Then look for another restriction. The second sentence says she feels that the amount invested in bonds should be at most 1/3 the amount invested in stocks. So bonds are at most 1/3 of the stocks. Well, the amount invested in bonds was Y, and that's going to be compared to 1/3 of the amount she invests in stocks, which is X. Well, I want the bonds to be at most 1/3 of the stocks. So that means that the amount invested in bonds can be less than the amount invested in stocks, but not greater than it. So this gives me Y is less than or equal to 1/3 X. The next thing you do is you always look back at the problem and look at what your variables were. And ask yourself, can those variables be negative? Well, our variables were the amount of money invested in stocks and bonds. So you ask yourself, can she buy a negative amount of stocks and bonds? And the answer is no. So for the stocks, that was X. X has to be greater than or equal to 0. And the amount invested in bonds was Y, so this gives us Y has to be greater than or equal to 0. This time my variables cannot be negative. So if I put all my restrictions together, I get a system of inequalities. I had the X plus Y is less than or equal to 40,000. Y is less than or equal to 1/3 X. And then X and Y both greater than or equal to 0. Now I want to graph each one of these inequalities. Let's begin with the first one. I'm going to have the boundary line X plus Y equals 40,000. This is going to be a solid boundary line because I had an equal to sign. So now I want to find my intercepts. For the x-intercept, let y be 0, and I get x is 40,000. So this gives me the ordered pair 40,000, 0. Next, for the y-intercept, let x be 0. If x is 0, I get y is 40,000. So this gives me the ordered pair 0, 40,000. For my second boundary line, I would have y equals 1/3 x. This is also a solid boundary line because my original inequality, less than or equal to, had the equal to portion to it. Now, if I find my x-intercept, I let y be 0. So I have 0 equals 1/3 x. Well, if I divide each side by 1/3, 0 divided by 1/3 is 0. So my x-intercept is 0, 0. Whenever the x-intercept is 0, 0, my y-intercept is also going to be 0, 0. For the y-intercept, if you let x be 0, you get y equals 1/3 times 0, which is just 0. So since my intercepts are the same, I need a second point. So I'm going to let x or y be any value. In this case, I'm going to plug a number in for x since it has a 1/3 in front of it. That number that I plug in for x, I'm going to make it be a multiple of 3. That way when I multiply it by 1/3, I'm not going to be left with a fraction. And instead of letting x be a 3 or a 6 or a 9, look at your intercepts for this first boundary line. Those values were 40,000. So to get my second point, I'm going to let x be 30,000. So go to y equals 1/3 x, and let's replace x with 30,000. Well, 1/3 times 30,000 gives me 10,000, so y equals 10,000. So my second point is the ordered pair 30,000, 10,000. Now let's look at graphing this. I first want to begin with x is greater than or equal to 0. This means I'm only using positive x values. So I don't need any of the x values to the left of my y-axis because those are all negative. So there will be no negative x values. When I draw my y-axis, I'm going to move it to the left side of the page. And since x cannot be negative, I'm going to shade or mark out those negative x values. Now let's look at y greater than or equal to 0. This means there will be no negative y values. So I don't need any of the y values below the x-axis. So I'm going to draw my x-axis low, and I'm going to shade or mark out all the y values below that x-axis. So basically, anytime you have x and y greater than or equal to 0, this restricts us to quadrant 1 of our coordinate system. Now let's look at our first boundary line, the x plus y equals 40,000. On my graph, I'm going to change the scale for these, and often with the word problem, sometimes you need to rescale your graphs. So I'm going to let every line represent 10,000. So my scale is 10,000. You need your scale to be consistent for every line that you graph. So to graph the ordered pair 40,000, 0, it's going to look like the ordered pair 4, 0, because each line represents 10,000. To graph the ordered pair 0, 40,000, that's going to look like the ordered pair 0, 4. Then draw a solid boundary line through these 2 points. Since that line does not go through 0, 0, I can let my test point be 0, 0. If I go back to my original inequality, x plus y less than or equal to 40,000, and replace x and y with 0, I end up with 0 is less than or equal to 40,000. That's true, so that means 0, 0 is part of my solution. So the area below my line or to the left of my line is the solution. The area above it is not the solution. So I mark out the part or shade the part that's not the solution. Now let's look at our final boundary line. The y equals 1/3 x. Well, my first intercept was at 0, 0. And the second point that I'm graphing is 30,000, 10,000. So remember, each line is 10,000. So the first line is 10,000, then 20,000, then 30,000. And then when I go up one, that gives me 30,000, 10,000. And I draw a solid boundary line through those 2 points. Now this time for my test point, I cannot use 0, 0 because the line goes through 0, 0. So I'm going to use 30,000, 0. That would be this point right here. So I'm going to plug in 30,000 for x and 0 for y. So go to the y is less than or equal to 1/3 x, and I get 0 is less than or equal to 1/3 times 30,000. Well, 1/3 times 30,000 is 10,000, so 0 is less than or equal to 10,000, and that's true. So that means this point right here, 30,000, 0, is part of my solution. So the area above that line is not my solution, so I'm going to mark it out. So now I have this triangle right here forms all my possible solutions. So I just label my solution area with the word solution. This time my solution area is bounded. It's sealed on every edge with a boundary line. So this would be an example of a system of inequalities that has a bounded solution. Well, let's look at some of Carla's investing options. Let's just consider any ordered pair in that solution area. So let's consider this point right here. Remember, each line represents 10,000, so the X is 30,000, and this looks about halfway between the 0 and the 10,000, so let's say Y is 5,000. So what does this mean? Well, remember, X was the amount that Carla invests in stocks, and Y was the amount Carla invests in bonds. So this means Carla could invest $30,000 in stocks and $50,000 in bonds. That combination fits her restriction. If I add them together, it's less than $40,000. So she has invested up to $40,000. And then the other restriction were bonds were at most 1/3 of the stocks. Well, if the stocks are 30,000, a third of 30,000 is 10,000, and the bonds do not exceed that. So this combination of investing options satisfies her restrictions. I could also use another ordered pair. Let's look at this point right here. And we'll just estimate that to be 20,000, 2,000. Or if you made that 20,000, 1,000, that would be fine. Just any point in that solution area. Well, this means Carla could invest $20,000 in stocks and $2,000 in bonds. So these are just her possible investing options. In the next couple of lessons, we're going to look at which of these combinations would be the best investing options based on what Carla wants for results with investing her money. So let's look at our next example. Richard's Toy Truck Company manufactures two models of toy trucks, a standard model and a deluxe model. Each standard model requires 4 hours of painting and 2 hours for detail work. Each deluxe model requires 2 hours of painting and 4 hours of detail work. There are 2 painters and 3 detail workers employed by the company, and each employee works at most 40 hours per week. What are the possible amounts of each truck that can be manufactured per week? Whenever you're given an application problem, always look for what you need. This is usually what you are asked for. We're asked for the possible amounts of each truck manufactured per week. So we need the amount of each truck that can be manufactured per week. Once we determine what we need, we decide what our variables are going to be. Well, we want the amount of each truck, and there's 2 types of trucks, so I'm going to have 2 variables. We're going to let X be the amount or the number of standard model trucks produced, and let Y be the amount or the number of deluxe model trucks produced. In the next step, you look for your restrictions. Look back through the problem. What is preventing this company from producing 1,000 of each truck each week, or 1,000,000 of each model truck each week? Well, if you look back, each truck has to be painted and has to be detailed, and they're limited to the amount of workers or the amount of hours those workers can work. So let's look at the painting first. The standard model truck requires 4 hours of painting. And if I'm producing X number of standard model trucks, that means for every one I produce, I need 4 hours devoted to painting. So I'm going to multiply the 4 times the number produced, and that gives me 4X. I also have to paint the deluxe models, and they require 2 hours of painting. Well, there are Y deluxe models produced, so I'm going to add to this my 2Y. Well, now I only have 2 painters, and they're going to work at most 40 hours per week. So the number of hours that I spend on painting, the 4X plus 2Y, has to be less than or equal to 2 times 40. The 2 workers times the number of hours, the 40 hours they're going to work. And the reason I used less than or equal to, it says they're going to work at most 40 hours, which means they could work less than 40 hours that week. They just cannot work over 40 hours. Well, if I go ahead and multiply that, it's going to give me 4x plus 2y is less than or equal to 80. Now let's look at detailing. Well, each standard model requires 2 hours for detail work. And if I'm producing X number of standard models trucks, this is going to give me 2X. Well, the deluxe models require 4 hours for detail work. And I have Y as my number of deluxe models produced, so this gives me plus 4Y. Well, I have 3 detail workers that can work up to 40 hours per week. So the number of hours I spend detailing these trucks, the 2x plus 4y, has to be less than or equal to the 3 times 40. And if I simplify this, I get 2x plus 4y has to be less than or equal to 120. Then the next thing you always want to ask yourself, can my variables be negative? Well, my variables were the number of trucks that I produced of the standard model and the deluxe model. I cannot produce a negative amount of trucks. So for the standard model, X has to be greater than or equal to 0. And for the deluxe model, Y has to be greater than or equal to 0. So now I have the 4 inequalities that make up my system. I have 4x plus 2y is less than or equal to 80. 2x plus 4y is less than or equal to 120, and then x and y are both greater than or equal to 0. So let's look at graphing these. I'm going to begin with the boundary line for my first inequality, and this is 4x plus 2y equals 80. Since my inequality was equal to, it's going to be a solid boundary line. To find my x-intercept, let y be 0. If y is 0, I have 4x plus 0 equals 80, or just 4x equals 80. So if I divide each side by 4, I get x is 20. So this gives me the ordered pair 20, 0. Then for my y-intercept, let x be 0. If x is 0, I end up with 2y equals 80. And if I divide each side by 2, I end up with y equals 40. So our y-intercept is the point 0, 40. For the second boundary line, we're going to have 2x plus 4y equals 120. And this is also a solid boundary line because the original inequality had the equal to part. For the x-intercept, we let y be 0, so this gives us 2x equals 120. If I divide 120 by 2, I get 60, so this is the ordered pair 60, 0. For the y-intercept, let x be 0, so I have 4y equals 120. If I divide 120 by 4, I get y is 30, so the y-intercept is the point 0, 30. So I'm going to begin by graphing the restrictions x is greater than or equal to 0 and y is greater than or equal to 0. As we mentioned before, if x is greater than or equal to 0, that means x cannot be negative. There will be no negative x values. So I'm going to draw my y-axis to the left side of my graph, and I'm going to mark out all the negative x values. So I'm going to shade to the left of the y-axis. If y is greater than or equal to 0, that means there's going to be no negative y values. So I'm going to draw my x-axis low on the graph, and I'm going to mark out or shade all the negative y values. So I'm going to shade below the x-axis. And as I mentioned before, if you have x and y both greater than or equal to 0, this leaves us in quadrant 1. Next, let's look at the boundary line 4x plus 2y equals 80. My intercepts were 20, 0, and 0, 40. So looking at all of my intercepts, the 20, 0, the 0, 40, the 60, 0, and the 0, 30, I'm going to let my scale be 10. So for 20, 0, I go over 2 lines and make my ordered pair. And for 0, 40, I go up 4 lines on my y-axis. And I draw a solid boundary line through these points. Now the line does not go through 0, 0, so I can test 0, 0. If I replace x and y with zeros, I'm going to get 0 is less than or equal to 80. And that's true. So always go back to the original inequality, the 4x plus 2y is less than or equal to 80, and replace x and y with zeros. Since 0, 0 was true, I'm going to mark out the area above the line. That would be the area that's false. Next, let's look at 2x plus 4y equals 120. If I have the ordered pair 60, 0, that means I go over 6 units on my x-axis and make a point. The y-intercept is 0, 30, so I go up 3 units on my y-axis and make a point. And I draw a solid boundary line through these. Again, this boundary line does not go through the ordered pair 0, 0, so I can use 0, 0 as my test point. So go back to the original inequality, 2x plus 4y is less than or equal to 120, and replace x and y with zeros. This gives me 0 is less than or equal to 120, and that's true. So the area below the line is true, so I'm going to mark out the area above the line. And now if you remember, the way we shade in this class, after you mark out the areas that are false, the area of your graph without a single shaded part to it is my solution. So my solution is the four-sided shape at the corner of my grid. Since it's enclosed on all sides with boundary lines, this solution is bounded. I'm just going to zoom in on that solution on the screen. And like the previous example, let's look at some possible solutions. Let's look at this point right here. If each line represents 10, that's the ordered pair 10, 10. So that means we could produce 10 standard trucks and 10 deluxe trucks. Another point in that solution area is the second point. That looks like we've gone over 5 units because it's halfway between the 0 and the 10. And then I've gone up 2, so that's 20. So this would be the ordered pair 5, 20. So this would mean we could produce 5 standard trucks and 20 deluxe trucks. Since all of my boundary lines were solid, I can also pick a point on the boundary line. If I look at this point, my x is 0 because I don't move off the y-axis, and I went up 2.5 spaces, which would give me 25. So that's the ordered pair 0, 25. So that means I could produce no standard trucks and 25 deluxe trucks. And again, these were just 3 possible solutions. What we'll do is eventually look at, of all of my possible solutions, which one would be the best solution.